Hi everyone. So our next lecture, what we're going to do is kind of continue on, and we are going to prove some set relationships and some set operations. One of the main things that we want to be able to do is prove when one set is a subset of another one. So going back to the original definition, we can prove that A is a subset of B by showing this if-then condition. So if we show that if X is an element of A, then X will be an element of B. So let's just write out the proof template for this. So the proof template would look something like this. So you'd write proof, and we're going to prove this if-then condition. So we're just going to suppose X is an element of A, and then you want to show X is an element of B. So at this point, you might use some properties or some other conditions that you might know about A, some restrictions, and that would then eventually you'd be able to get X is an element of B. So that's sort of our basic template for this. Similarly, we can write out a proof template for when two sets are going to be equal. Effectively, what we're just going to show, if we want the set A to be equal to the set B, we'll prove that A is a subset of B and B is a subset of A. So we'll pretty much just be doing the proof template up above twice. So a basic template for proof for this, your template would look something like this. So you're going to effectively have two parts of this, and one way you can kind of symbolically write this is you're going to, you could write it like this to show A is a subset of B, and then kind of writing the subset inclusion the other way, you're going to show B is a subset of A. So each of these kind of have their subproofs which follow the template that we just did up above. So you would say, suppose X is in A, and then you would show X is in B, right, as an element of B. So you do a bit of work here. You get X is equal to B, and then you would effectively have one part of this. And to go the other way, you would just do the exact same idea, right? So you would suppose you have an element of B, and then you want to show that element belongs to A. Okay, so you do a little bit of work here. X is B and A. And then now that we've done both of these, we'll be able to say that these two sets are equal. Okay, so let's look at a specific example. So suppose that I give you the set A, and I say in set builder notation, we could read this as X is an element of the integers such that X satisfies this condition. The condition is that X is congruent to 2 modulo 5, or 2 mod 5, you could read it that way. And B is going to be the set of integers that are congruent to 7 mod 10. And the question is A a subset of B? Is B a subset of A? Could you prove or disprove each of these statements? So I think probably the best way to start this would to be at least to kind of better understand what these two sets actually look like. So what would it look like to have an element in A? So let's just consider real quick. Consider an element X in A. So what conditions would it have to satisfy? Well, if X is in A, then we know that it's an integer and X is congruent to 2 modulo 5. So by definition of this congruence relationship, we know that this means X minus 2 has to be equal to 5 times some integer. So we could say X minus 2 is equal to 5j for some integer j. Okay, so kind of can get an idea of what X looks like. We could kind of solve for X, right? You could bring this 2 over here, so then we have 2 plus 5j for some j. Okay, and this j can be any integer. So it effectively looks like X, you kind of start at 2, and you're sort of adding or subtracting a multiple of 5, right? So in other words, so A, you could actually write out the elements in sort of a roster list form, right? We could write it out like this. You could say you have 2 plus 5 times negative 1. You could have 2 plus 5 times 0. You could have 2 plus 5 times 1, 2 plus 5 times 2, and so on, right? So here, what I'm doing is I'm just adjusting our j value. So j is negative 1, 0, 1, and 2. And then you could simplify this a little bit, and so what will we have? We'll have 2 minus 5 So I have negative 3, 2 plus 0 is 2, and we'll have 2 plus 5 is 7, and 2 plus 10 is 12, and so on. So you can see that you're kind of starting at this value of 2, right? And you're just adding or subtracting 5. So you're just adding 5 to go to the right, and subtracting 5 each time to go to the left. So we kind of have a better idea of what the elements of A actually look like by doing this. Similarly, you could do that for B, right? So if we consider x is an element of B, then what would that mean? Well, x again would be an integer, and x would be congruent to 7 modulo 10. So in this case, we'll have to write x minus 7 is 10 times an integer. So we could use, say, L, right, for some integer L. And then we could play the same trick, right? So you could solve for x, bring this 7 over. So effectively what you're kind of doing is you're starting at 7, and now we're going to either add or subtract multiples of 10 to this, right? Okay, so then B will be pretty similar, right? So we're going to have these elements. We'll have 7 plus 10 times negative 1, 7 plus 10 times 0, 7 plus 10 times 1, and 2, and so on, right? So B will have 7 minus 10, right? So minus 3. Okay, and then we'll have 7 plus 0, right? So this is kind of like your starting value, right? So here we subtracted 10, now we're going to add 10. So we'll have 17, right? 7 plus 10, and so on, right? 27, whatnot. Now modulo 10, right? Modulo 10, if you're kind of thinking of the positive ones, then these are the ones that are going to have in the ones digit, right? It's going to be a 7, because modulo 10, you're just going to be subtracting off 10 over and over and over, right? So we have kind of a better idea of what B looks like. Okay. Now, looking at these two sets, you can re-ask this original question, right? Is A a subset of B? Is B a subset of A? Prove or disprove each of these statements. Now, actually looking at the roster form can give you kind of an idea of that. If you kind of stare at A, for example, if I want A to be a subset of B, then I have to have every element of A over here would have to be contained over here. So for example, this 2 is an element of A. Is 2 an element of B? Well, it doesn't appear to be in this list, right? And similarly, if you, but I do have some things in common, right? I have 7 is in A and 7 is in B, okay? But what about going the other way? So if I pick an arbitrary element of B, is that contained in A? Well, it looks like 7 is in B, 7 is in A. What about 17? Well, I have 17 in B, and 17 would be actually an A, right? Because if I added another 5 here, that would get me to 17. So it just kind of, at a glance, it looks like B probably will be a subset of A, and it looks like A will not be a subset of B, and we can provide a counterexample for that, right? So we can immediately say, we can use that idea to get this, right? So here's the question. So is A a subset of B, right? So that's the question. Okay, well, it looks like that's no, right? Because to be a subset, I have to be able to pick any element I want in A, and I have to show that it's in B. But we can provide a counterexample to this, right? No, consider 2, which is an element of A. 2 is not an element of B. And how do we know that? Well, we're looking at the roster form, but could we actually prove that using the original definition? Well, we could kind of assume what would happen, right? You can, by way of contradiction, right? So since if 2 was an element of B, what would that mean? We would have remember, elements of B satisfy this equation here, right? So we would have to have that 2 minus 7 is equal to 10L for some integer L. Okay, well, what happens to this? Well, then you'd have negative 5 equals 10L. And then that would tell you, well, we divide both sides by 5, and you have negative 5 over 10 is equal to L, and this is, what is this? This is negative a half, right? Negative a half, well, that's certainly not an integer, right? So that's sort of a contradiction, right? So thus, this assumption is not possible. So 2 is not an element of B, right? And well, how about going the other way? It looks like the elements of B are contained in A. So that seems, at least no immediate counterexample is clear from that. So staring at this a little bit, it seems like we could go back and we can use our template up here to prove the subset inclusion, right? So if we try to answer this question, so is B a subset of A? Okay, well, it looks like the answer is going to be yes, but let's attempt a direct proof, right? So we'll kind of jump the gun here and say that it is yes, right? But let's try to provide a proof, right? So let X be an element of B, right? And then we have to show X is an element of A. Those are the requirements, right? If you want to show B as a subset of A, we have to satisfy this if-then condition, right? So we're going to assume X is in B and show that it's in A. So if X is in B, then we know it must satisfy this condition, right? By definition, the elements of B are congruent to 7 modulo 10. So we know that an element of B will satisfy this condition, right? So X minus 7 is equal to 10L for some L. Okay, now what does it mean to be an A? Well, that means that we have X satisfy another type of equation, right? So we have to actually show that X satisfies this equation, right? So X minus 2 is equal to 5J for some integer J. Okay. Now I'm just translating, right? So this is what I was talking about before. Once you make this assumption that X is an element of B, that will mean something. So it means this equation has to be satisfied. If you want to show X is an element of A, then we have to show this equation is satisfied. So we're using the definitions to progress a little bit here, right? Okay, so now solving for X, what do we have? We know that this will be 7 plus 10L, right? But what are we interested in? We're actually showing that X minus 2 is 5J. So now that I have X, we could actually try to figure out what is X minus 2. So now X minus 2 would be what? It would be, we could essentially substitute, right? So this, we can substitute for X. So we'll have 7 plus 10L minus 2, right? So we're just making a substitution that X minus 2 would be equal to this now. And you can simplify this a little bit. So X minus 2, remember, we're still interested in what X minus 2 is. We want to show that it's 5 times an integer. So let's see what happens to the right side of this equation. Well, if I subtract 2 from the 7, then I get 5. So I have 5 plus 10L. And then now, if you look at the right side, I have X minus 2 is definitely 5 times an integer, right? Because I can factor this 5 out. So if I factor 5 out, I have 1 plus 2L. And this right here, this 1 plus 2L is definitely an integer since L was an integer, right? So what does this tell us? So we're done, right? We've satisfied the requirements. We have X minus 2 is 5 times an integer. So we are actually done. And if you want to polish it a little bit, we could say now X is congruent to 2 modulo 5, right? That's the same thing as saying this, right? We have X minus 2 is 5 times an integer. So X is congruent to 2 modulo 5. And therefore, thus, X is an element of A, right? So that would be kind of a nice proof for this. Okay, moving on to some properties, so some set identities. Well, there are a lot of set identities that are analogs of what we had before with the and or logical operators, right? So for example, we do have identity laws for sets. If I take a set and I union it with the empty set, I'm not going to add anything else to the set. That's why I'll get back A. Similarly, if I took A and I intersected it with the whole universe, remember, the intersection is what's common among both of them. I have to be in A and the universe. Well, that's just going to give me A back. Right? So the identity laws are not that shocking. Similarly, these domination laws, if I took A and I unioned it with all the universe, remember, you're kind of combining these lists in a way, right? So of course, this is going to make it the whole universe. And if I took A and I intersected it with the empty set, what's common among both of these? Well, the empty set doesn't contain anything, so I'm only going to get the empty set there. The idempotent laws, this is just what happens if you take a set and you union it with itself or intersect it with itself. When I take the union, I'm not going to get anything new, right? I'm just going to get A. Similarly, if I intersect A with A, what's common among both of them? A, element of A and A, well, I'm going to get back A. So if I have an or an and here, it's not going to make any difference. Complementation law, this is not very shocking. If you take a set, you complement it, and then you take that complement, you'll get back A. So the double complement will get you back. Again, these all have analogs to the logical operator. So in a sense, this is the analog of if you take the negation of a logical statement and then you negate that, so a double negation, you'll get back to the original statement, right? You have commutative laws. It doesn't matter if I do A union B or B union A. I'm going to get the same set. And that's because OR has this commutative property. Similarly, AND has that. So the intersection will definitely have that. You have associative and distributive laws, just like you did with the logical operators. And you also have a De Morgan's law for sets, right? Which is really nice because now you have this analog. And we'll actually prove the one of these. We'll prove the first one, I think. You also have an absorption law. You can kind of think of this a little bit. If you took A and now I union it with A intersect B would, in general, well, not every time, but in most situations, if you intersect two sets, you're going to get something smaller, right? And then if I union back with A, I'm just combining these lists, I'm going to get back A, right? So the intersection is contained in A, right? So when I union it back with A, I'm going to get A back, okay? And then if I took A intersect this union, okay, this in general could be something a little bit bigger, like a bigger set, but once I intersect back with A, I'm going to return with A. If you kind of draw some pictures for these, you'll convince yourself of them. Of course, you could formally prove them. And if you want some practice, of course, please do that for all of them. It would take a little bit of time to prove every single one, but they're really not that horrible. If I took the union of A with its complement, you'll get back the whole universe. That's not too bad. If you just look at a picture really quick, you can convince yourself of that. And if I intersect A with its complement, they're not going to share anything because remember the complement is what's outside of A, right? So if I intersect them, they're not going to have anything in common, so that'll give me the empty set. That's why this one, you give you the whole universe, right? If I take A and then I take the complement, I'm looking at the stuff in the universe outside of A. So I'm essentially combining these two lists and I'm going to get the whole universe. Okay, so let's try to prove this first De Morgan's law that's up above. Now, before we actually formally prove it, I think it might be nice to actually kind of draw some pictures to see if you're convinced intuitively kind of using the pictures here. So this is kind of saying if you take the complement of the intersection of A and B, you will actually get the union of the complements of A, the union of the complement of A and the complement of B. So just to kind of show this, why don't we try to draw some pictures here? So if I have A and I have B, and let's draw the intersection. So the intersection would be this, right? So this would be A intersect B. Okay, well, what would the complement of this look like? The complement would look like this. So I have A and B, and then I would be looking, the whole square is the universe, right? So what's outside of this common region? You know what, let me switch to maybe another color here. Okay, so it would be everything outside of that, right? So I would have everything that's not within this sort of overlap, right? Okay. So our claim is that this right here, which is the complement of the intersection, right, should be the union of the complement of A and the complement of B. So why don't we draw a picture for the complement of A and the complement of B and see if we get this. Okay, so let me switch back real quick. Okay, so back over here. So we have A and we have B. Okay, so what would the complement of A look like? Well, that would be everything that's outside of A, right? So outside of A, outside of A, right? So this is the complement of A and the complement of B. Okay, everything outside of B. Okay, and if you stare at this a little bit, if I take this collection and I union it with this collection, look, they're not going to have, both of these do not have anything within this common intersection up here. But the complement of B definitely contains the stuff within A, right? Just not what's in the intersection of the two, right? And the complement of A contains what's in B except for what's in the complement of these two, as well as the stuff outside. And you will get this region up here. So, right, this is actually going to be the union of the complement of A and the complement of B. So this looks fairly intuitive just from the pictures, but we'd like to actually formally prove this. Okay, so if we want to prove that these two sets are actually equal to each other, then we have two things to do, right? We have that template up above which says we're going to have to show that the set on the left is a subset of the set on the right, and the set on the right is a subset of the set on the left, right? So it's actually kind of two subset inclusion proofs, okay? Okay, so let's just start. Okay, so proof. So if we're going to show this way first, we are going to show, okay, so down here you can write show that if I take the complement of the intersection, this is going to be a subset of the complement of A union the complement of B. Okay, that's going to be one part of the proof. So, and we're going to have two parts total. Okay, so first, how do we do this? Well, the template for subset inclusion says you're going to assume you pick an element on the set on the left here. So assume that X is an element of the complement of the intersection of A and B, and then we're going to show that X is an element of A complement union B complement. Okay. Now, well, what would this mean? Well, as soon as I assume that X is an element of this set, it must mean something, and by definition, we do have a definition for this, right? So if we're saying we're in the complement, then we could say that is X is not an element of the intersection. Okay, but what is this intersection? The intersection is the collection of x's, right, such that X is in A and X is in B. All right, so thus, right, if X is not in this, okay, then what can we say? Well, we could say that X is not in A or X is not in B, right? So effectively, we're using the De Morgan property of satisfying the negation of this, right? So if you negate this, you will get x is not an element of A or x is not an element of B, right? Because we want x to not be a member of this intersection. So this is effectively by De Morgan again, but it's a logical De Morgan property, right? Okay, so what would it mean for x to not be an A? That's the same thing as saying x is, so hence x is an element of the complement, right? If you say x is not an A, then it's in the complement. And we still have this or x is in B complement, all right? Well, look at what we have right here. You have x is an element of the complement of A, or x is an element of the complement of B. By definition, you're saying that x is an element of the union of A complement and B complement, right? Because that's what the union would be by definition. The union would be that x would have to be an element of the set on this set or this set. That's what this would mean. Okay, so and we're done, right? So we wanted to show this. X was an element of A complement union B complement. And now let's just go the other way and see if the same thing happens. Okay, so now we are going to prove the subset inclusion the other way. So we are going to show that the complement of A union the complement of B is a subset of A intersect B complement. Okay, so we'll start out the exact same way. So let x be an element of A complement union B complement, and then you want to show again x will be in this set now. So the intersection of A and B, the complement of that. Okay. Okay, so what does this mean? So by definition, x is in the complement of A or x is in the complement of B. All right, so now if you get to a situation where you know x satisfies sort of the, you have an or condition here, right? X is in complement of A or it's in the complement of B. This is a perfect situation where you can kind of just explore the two cases here, right? You have cases to deal with. You either have this situation or you have this situation. So if we're in this situation, do we get the conclusion? And if we're in this situation, x being in B complement, do we get the conclusion, the effective conclusion? Okay, so let's look at that. Okay, so case 1. X is in the complement of A. So if x is in the complement of A, what does that mean? Well, by definition, we can say that x is not an element of A. Okay, if x is not an element of A, does that help us in any way? Well, we want x to be an element of the complement of A intersect B. So if x is not an element of A, what does the complement of A intersect B look like, right? So since A intersect B, what is that by definition? So this would be the collection of things that look like this. X such that x is in A and x is in B. Right? X would have to be an element of A and x would have to be an element of B. This is what the intersection would look like. So if you're already saying that x is not an element of A, then it clearly does not satisfy this and condition, right? You would have to satisfy both of these things for this to be true, for you to have an x like this. So it must be that x is not an element of the intersection. So if x can't be in the, if x is not an A, certainly it's not in the intersection. You could have actually just jumped right here to this, right? The intersection is even more restrictive, right? So x is an element of the complement then. As soon as you can guarantee that it's not in this intersection, then it would be a member of the complement, and that's what we're after here. Okay, could we say the same thing in the other case? Well, case 2, x would be an element of B complement. So then x would not be an element of B. Okay. Well, similarly, the intersection is still the same, right? So in order to be in the intersection of A and B, I have to have x is an element of A and x is an element of B. Down here, I'm saying that x is not an element of B. So by definition, it must be that x is not an element of the intersection. So again, x would be an element of the complement. Okay? And in either case, we ended up with the correct conclusion, right? So in either case, x was an element of the complement of A intersect B. Okay? All right, so we prove both of these subset inclusions, both directions, so that concludes that the two sets are actually equal to each other. All right, so if you want, you could even end with that, right? Thus, A intersect B complement is A complement union B complement. Okay, that's not really necessary to add this conclusion remark right here. I mean, you did the two subset inclusions here, and it's pretty clear that we were trying to prove that from the beginning. Okay, so let's see if we can prove the first distributive law. So let's show that these two sets are equal. Similarly, we are going to have to do the subset inclusion in both ways. Now, instead of writing out show this set on the left is a subset on the set on the right, let's just actually try to write out the template immediately, right? So let x be an element of the set on the left, and we are going to show that x is an element of the set on the right. So this would be A union B, and then we're going to intersect that with A union C. All right. So here, again, we're going to have to know the definitions, right? So in order to say, well, what does it mean for x to be an element of this set on the left? Well, x is an element of A, or, right, so this union translates to an or effectively, right? Or x is an element of this set. So B intersects C. And if you want, a good strategy might actually be to translate what you're showing as well. So show x is, well, what would it mean for x to be an element of this intersection? It would mean that x would have to be in this set and this set. So this would be x is an element of A union B, and x would be an element of A union C. Okay, so can we take this a little bit further? Well, we could definitely break this one out, right? But let's just look at what we're trying to show first instead of further writing this out. I mean, if you want A to be in this union and you want if you want x to be in this union and you want x to be in this union, what does that mean? So so show, okay, so this is going to be an or, right? This would say x is an element of A, or x would be an element of B. Okay, so we want this or, and you'd have another or, right? You'd have x is an element of A, or or x is an element of C. Okay, so just have to be a little bit careful here. So you want these two conditions to be both true, right? Because this is an and, right? But within this, you have an or. So you want at least one of them to be true. Okay, well, coming back over here, look at what you have. You have x is an element of A, or x is an element of B intersects C. Now, we effectively have two cases to deal with, right? So, because we have an OR here. So case 1, x is an element of A, right? And then case 2, x would be an element of this, right? So this right down here, we'll write case 2, x is going to be an element of B intersects C. Okay, now if x is an element of A, do we get this whole thing as true? Well, look at the first part. So if x is an element of A, then certainly x is an element of A or x is an element of B is true, right? If we have x is an element of A, then this OR is true, right? Because we have the x is an element of A is definitely true. And it doesn't matter if this x being an element of B is true or false. This OR will definitely be true. And this other OR is true, right? We have x is an element of A or x is an element of C is also true. Okay, so we have both of these components are true. And for an AND to be true, you want both of these to simultaneously be true. So we're done. So thus, x is an element of A union B intersect A union C. Okay, does the same thing happen down here? Well, down here, this would imply, if you're in the intersection, then we actually know x is an element of B and x is an element of C, right? So similarly, looking up here, this would imply x being an element of B will imply that the first OR is true, right? It would imply x is an element of A or x is an element of B is true, right? That would be implied by the x being an element of B. And the second part, x being an element of C, would imply this OR is true. X is an element of A or x is an element of C is true. And again, we have both parts are true. So and when you take an AND, you want both parts to be true. Thus, this AND statement is valid, right? So now we can say x is an element of this intersection. So thus, x is an element of A intersect B. That's actually a union, right? So x union B intersect A union C. Okay. So, I mean, it's the complicated parts is really just kind of understanding the definitions. What do these things translate to? And slowly progressing, right? So we had an OR that translated into these cases. And what we had to show, we could break that out and slowly show what are some things that we want to show are true and deal with them individually. Okay, now technically we're not done yet, right? Because we've only done one half, right? We have to actually show still the other implication. So this is actually kind of a long problem, right? So the other implication going this direction instead, okay, going back up to the top, we're going to pick an element of this set, and we're going to show it's an element on, pick an element on the right set, show it's an element of this set on the left. So start out with the same strategy, right? Let x be an element of A union B intersect A union C, and then now you're going to show x is an element of A union B intersect C. Okay. Well, again, the strategy is just going to be to write this out by definition. Now, we have done that actually already, so we kind of already have the components written out. X being an element of this huge intersection here is going to mean this, right? So by definition, we can write this whole thing out, and then you're going to show this is satisfied, this OR. So let's just do exactly that. So you can really just write by definition And you can write this exactly. Okay, and then you want to show this. So x is an element of A, or x is an element of the intersection. Okay, so just kind of translating again by definitions. Okay, now this is what we're after. Maybe we could give this this thing up here. Let's just call this star, because we're going to kind of refer to this. All right, if you don't want to keep writing something out, you could kind of give it a name. So let me just call it star for a second. And look at what you have over here. You kind of, if you dissect this, we have an or and an or. So we actually have essentially a bunch of cases to deal with, right? So let's look at each of these cases individually and see if we can get the conclusion. So case 1. Okay, for an and to be true, I have to have both of these are true, right? But for an or to be true, I only need one of these to be true, at least one, right? So one case would be x is an element of A, right, which would make this true, and x is an element of A. Well, it's kind of saying the same exact thing, all right? Case 2, okay, well, sorry. If x is an element of A and x is an element of A, is this star true? Well, when you want an or to be true, you only need one part of it to be true. And if you look over here, the first bit is definitely satisfied. I don't even have to look over at the second part. Look, I have x is an element of A. So therefore, star is definitely true. Right? I can actually write that. So star, whoops, sorry. So star is true, right? Since x is an element of A, right? This is satisfied, okay? So similarly, what happens with the other, what are some of the other cases? So case 2, we could have x is an element of A and x is an element of C. Case 3, we could have x is an element of B and x is an element of A, right? And then case 4, you could have x is an element of B and x is an element of C over here. Whoa. And x is an element of C. Okay, so these are kind of your 4 cases if you want this and, right? All right, well, in this first one, again, you have x as an element of A, so star is going to be true again there, right? So star is true. Since x is an element of A, right? If I'm saying x is an element of A and this condition, I don't even care about this extra condition. Look, I know x is an element of A. So this first part of the or is definitely true. So the or will be true, right? So the whole star condition, that statement, that logical statement is true because I know x is an element of A is true. What about this one? If I know x is an element of B and x is an element of A, again, I know x is an element of A. So this or is going to be true. So star is true, again, since x is an element of A. Okay, so the first 3 cases are all true because in all these cases I knew x was an element of A. What about this case 4? Well, I don't have that, right? I have x is an element of B and x is an element of C. So I'm going to have to still make this or true. So the first part, I don't know any information about this, right? I don't know if it's true or false. But if you look over here, I could, the alternative is to show x is an element of this intersection over here, okay? So, oh, you know what, this is just, I made a minor typo right here. Do you notice that this actually should be a B here? That was just, I accidentally just wrote A there instead of B, right? Because this says A union B intersects C. So it's A, x is an element of A, or x is an element of B intersect C. We didn't do that up above, right? That was just a minor typo. Yeah, see, I just accidentally copied the wrong letter down. Sorry about that. I mean, so what does this tell us down here? So if x is in B and it's in C, then by definition, x would be in the intersection. Right? X is in B and it's in C, then x would be in the intersection, and thus we have that star is true again, right? So star is true. Okay, because we have this, right? So x is an element of this intersection. So this OR statement is true. And it doesn't matter, we don't have to know anything about it being an element of A or not, right? If this is true or false, this OR statement is still true because x is an element of the intersection is true. Okay, so now we've covered all our cases. There are no other cases. So you could just say thus by, in all four cases. So thus, all cases give x is an element of A union B intersect C. So we're done with this. And therefore, since we've shown both subset inclusions, you could write a conclusionary remark down here, but you could just kind of end the proof, and that's fine. You don't have to actually write a conclusion sentence, which would just say, you know, these two things actually show these sets are equal. Okay, finally, let's show these two sets are actually equal. So same strategy, we could still do the exact same thing that we did before. You know, you're following our proof template. So let's prove we're showing two sets are equal. So we're going to show subset inclusion both ways. So let x be an element of the set on the left here. So A minus C. It's a set difference, right? And then you're going to show x is an element of the set on the right. Okay. Now, what does this all mean? Well, you could start to write out what each of these mean by definition. So this is effectively saying, by definition, x is an element of the set difference, A minus C, and x is an element of the set difference, C minus B. But what about this show here? If you say x is an element of the empty set, such an x will never exist, right? Because the empty set does not contain any elements. So in other words, you're really kind of showing that x does not exist, right? X does not exist. Okay? Well, does that follow from these definitions? Well, what would it mean for x to be an element of A, the set difference of A minus C, right? So this would mean, by definition, x is an A, and x is not in C. Okay? And then this one, so we still have an and here, right? This would also, this set difference would mean x is an element of C and x is not in B. All right. Now look at all of this together. We have nothing but ands here. So all of these conditions have to simultaneously be satisfied, right? And do any of these lead to a contradiction, like a problem of x? It's impossible for such an x to exist. Well, look at this. I want an x in A. I want an x in C. I want an x that's an x that's not in C. I want an x that is in C, and I want an x that's not in B. Well, these two right here are the problems, right? I cannot have an element that's in C, an element that's not in C and an element that is in C, right? So x is an element of C and x is an element of C is this is always going to be false, right? Because these are negations of each other, right? So x does not exist. Right, this right here is always false. And the reason is because these two are negations of each other, right? Logical negations. So x, it's impossible for an x to exist, right? That'll satisfy this whole thing. Okay? Now going the other way, This one actually is a little bit faster because you really want to show here. Now you could do it by our normal template, but think about what you're actually showing. You're showing that the empty set is a subset of A minus C intersects C minus B. Okay, now I can totally use the template here and start it out that way. But look at what you have. You're trying to show the empty set is a subset of something. Well, we had a theorem in class that said that we already proved this, right? That the empty set is always a subset of any set that's given to me. So no matter what the set looks like, I always have the empty set and the original set are these sort of trivial subsets. So I can actually just finish it with that. The empty set is a subset of all sets. So we're automatically done. And mainly you can recall that previous theorem as well. You could, of course, do this by definition, right? If you say let x be an element of the empty set, show that x is in here, well, it becomes, you go back to the vacuous truth situation, that if part, this is always going to be false, okay? And the implication will be true. It's one of those false, if-thens. If the if part is false, this is a vacuous truth, so it'll result in the if-then being true.